Hi everyone. Today's topic that we're going to cover may be a little longer than the other videos because we're going to talk about something that's very basic but very important in statistics. Today we're going to talk about hypotheses, error, and p-values. So let's dive right into hypotheses. So I'm going to cover two types of hypotheses. The first is the null hypothesis, which we represent by H sub 0. And the second is the alternative hypothesis. And we represent that by H sub A. All right, so let's talk first about the null hypothesis. This is not the one you typically think of whenever you're trying to form questions for a scientific experiment. However, null hypothesis basically means that there is no difference among the means of our groups. Or just say no difference among groups. So an example of this could be, say I'm looking at plant height at different populations in different states. So my null hypothesis would be the height of plants at our West Virginia site are not different than the height of plants at our Kentucky site. So, in a quick way to put that, height at WV equals height at, height at KY. So that's just saying there's no difference among those two, the height of the plants at those two populations. So the null hypothesis is what we are worried about the most in statistical testing. We're testing our null hypothesis when we run our analyses. But the alternative hypothesis is one that we're more accustomed with. It's basically forming the question. So alternative hypothesis is there are differences among groups. So there are differences among groups. So what would that mean for our example? Well, that would say the heights of the plants at our West Virginia site are different, either smaller or larger, than the heights of the plants at the Kentucky site. So our alternative hypothesis is that height at West Virginia does not equal height at Kentucky. So as I said, when we're forming questions to test, we typically think of the alternative hypothesis. When we observe something in nature, we typically say, oh, I think there's a difference between these two groups or among these groups. But the null hypothesis, saying there is no difference among groups, is what we're testing in statistics. So that's about it on the types of hypotheses. But now I want to move on to error. So everything I talk about today is going to be intertwined. So make sure whenever you're thinking about error, you think about the hypotheses as well. So statistics worries about error quite a bit. And there are two main types of error that we talk about in statistics. The first is type 1 error. And the second is type 2 error. Now, we're not going to focus on type 2 very much. I'll give you a definition, but we're really concerned with type 1 error. So what is type 1 error? Well, the technical but a little hard to understand definition of type 1 error is rejecting the null hypothesis. And again, null hypothesis is H sub O, when in fact the null hypothesis is true. So type 1 error is when we reject our null hypothesis when in reality the null hypothesis is true. Now, that's always a little bit confusing to me, so let's talk about maybe an easier way to state that. So, an easier way that I like to say this is a type 1 error is saying there is a difference among means when in reality there is no difference. So, saying there is a difference among means when in reality there is no difference. Okay, so that's type 1 error. So what's type 2 error? Well, type 2 error is kind of the opposite. It's accepting the null hypothesis when in fact the alternative hypothesis is the one that's true. Okay, so accepting the null hypothesis when in fact the alternative hypothesis is the one that's true. So in other words, this would be saying that there is no difference among the means when in reality and unbeknownst to us, there actually are real differences. So someone actually sent me a website this morning telling me a great way to remember the difference between type 1 and type 2 errors because these are often confused. So never confuse type 1 and type 2 errors again. Just remember the story of the boy who cried wolf. Well, the boy who cried wolf caused both type 1 and type 2 errors in that order. First, everyone believed that there was a wolf when there really wasn't. That's our type 1 error. Next, they believed that there was no wolf when there really was. That's our type 2 error. So if you think of it this way, and you think of it in this order, you can simply substitute the word effect in for wolf, and you're done. So let's look at an example of this, and I call this the courtroom example. So say we're in a courtroom, and we have the truth, the real world truth, and then we have the verdict of the jury. So this is the actual truth, and this is what the jury decided. So let's say the truth is that a person is not guilty or guilty, and verdict is the same thing, not guilty or guilty. All right. So, if the truth is the person is not guilty and the jury comes to the verdict that the person is not guilty, we're good. That's fantastic. Similarly, if the truth is that the person is guilty and the jury decides that person is guilty, well, that's good for everyone else, maybe not for that guilty party, but we got the correct result. If the truth is that the person is guilty, but the jury decides he is not guilty, he or she is not guilty, we get type 2 error. Type 2. And that's where a guilty person is set free. And that's not good, right? But like I said, we're not going to be concerned with this for this histoprogram. We're worried about type 1 error. And that would be represented by a verdict saying someone is guilty when in fact they are not guilty. So that's type 1 error. And that's where an innocent person is jailed. All right. So that's just a very basic real world example of type 1 and type 2 errors. So whenever we do our statistics, we are focused on type 1 error, like I said, and we control for type 1 error by using something called p-values. So when we do a statistical test, we're going to get a couple of things. First, we're going to get a test statistic, and that could be an F statistic if we're doing an ANOVA, a T statistic if we're doing a t-test, R squared, um, chi-squared. Those are just some examples. But we also get an associated p-value with our test statistics. And this p-value is really important because it lets us know how to interpret our analyses. So what is a p-value? Let me clear this. A p-value is very simply the probability of committing a type 1 error. All right, so p-value is the probability of committing a type 1 error. So let's put that simply again. It's the probability of saying there is a difference among means when in reality there is no difference. And we want to control for that. So we do that by setting something called an alpha level. And you don't need to worry about what alpha level means, but I just wanted to let you know what it's called. And in science, we typically set that at about 0.05. So we judge our p-value based on this alpha level of 0.05. So just like no person is perfect, no experiment is going to be 100% perfect all of the time. So as scientists, we're okay being wrong 5% of the time. So 5% wrong equals okay for us. All right? So whenever we're analyzing these statistics and we're looking at our results and we're trying to determine how to interpret our results, we use 0.05 as a cutoff point. And this is representative of the cutoff point of the p-value. So if our p-value is less than 0.05, it means we have significance. And I don't like using the word significance because if we have a p of less than 0.05, what that really means is that we are confident in saying we see differences among our groups or in the means of our groups. Okay? So again, p-value is the probability of committing a type 1 error. So if our p is less than 0.05, that means we have less than 5% chance of committing a type 1 error, or less than 5% chance of saying there's a difference among means when in reality there is no difference. And we're okay with that number because it means we're wrong less than 5% of the time. All right, what if our p-value is between 0.05 and 0.1? Well, then we say we have a trend. We see a trend in our data. So, for example, we see a trend such that there may be differences among groups. Or maybe a better way to say it is a trend suggests that there are differences among groups. So in this scenario, we know we're between 5%, we will be between 5% and 10% wrong in saying that that we have differences among our means. So we call that a trend. However, anything above 0.10, Any p-value above 0.10, we say there's no significance. And we say that there are no differences among groups. Okay? So, p-value is the probability of committing a type 1 error. A type 1 error is saying there is a difference among means when in reality there is no difference. So the p-value is a probability of saying there is a difference among means when in reality there is no difference. And we want to keep that probability low, below 5%. And that's when we're comfortable in saying there's a difference among our groups. So just like we did the courtroom example a minute ago, let's go ahead and do a scientific example. So let's draw this same square, if my pen will work. Draw it a little bigger this time. All right. I'm going to switch the colors up a bit. All right, so let's say that on top we have a sample population. And on the side we have the actual true population. Okay? All right, so let's say for this actual true population, the null hypothesis is true. In other words, there really is no difference among groups. Or the null hypothesis is false, and there are differences among groups. This would also be our alternative hypothesis. So let's say for the sample population, and this is the population that we run our stats on. So this is the group we run our stats on, and we're trying to make inferences about the bigger true population. Let's say here we accept the null hypothesis. So that means that we have accepted the null hypothesis saying there is no difference among means. That would give us a p greater than 0.05. And here we reject our null hypothesis. And we would do this whenever we had a p-value lower than 0.05. And keep in mind this 0.05 is what we call alpha. All right. So let's say that the null hypothesis is true. There are no differences among means. And we accept this null hypothesis saying, yeah, we really did see no differences among means. Well, that's wonderful. We got the correct answer. Let's say the null hypothesis is false and there really are differences among means. Well, in our sample population that we ran our stats on, we rejected the null hypothesis. So we did well there also. What if the null hypothesis is false and there really are differences among groups, but in our statistics we said, well, there are no differences among groups. We accepted the null. This would be type 2 error, which again we're not worrying about. But what we are worrying about is if the null hypothesis is actually true and there really are no differences among means, yet when we run our stats, we reject the null hypothesis and we say there are differences among means. That's when we get type 1 error. And that's why we like to control for this type of error. Okay, so this is bad. We don't want this. So we make sure to set our alpha at 0.05. We do as much sampling as we can do to get a good idea of the actual population based on our sample population that we look at. So for example, we can't look at all men and women in the entire world, but we can look at a subset, which is our sample population. Now, one of the unfortunate things about this is you're never going to be 100, you're never actually going to know for certain um, whether you got the exact right answer, whether you have types of error. This is just a theoretical construct that we're trying to overcome by doing controls such as an alpha level. So if you have any questions about that, please ask Summer or your instructors, and I'll see you next time.